Okay, let's dive into this. Welcome to this explainer for Module 02 of our Cryptocurrency and Web3 course, where we're going to see how blockchain technology works under the hood. Today, we're definitely not just skimming the surface. We're rolling up our sleeves and taking apart the blockchain engine to see exactly what makes it tick. We're going to look at the nuts, the bolts, and the real cryptography that makes this completely revolutionary technology function safely and securely. Here is our roadmap for today's deep dive. We'll start with the decentralized digital ledger, then move inside the block anatomy. Check out the immutability mechanism, take a quick stop in the mempool waiting room, and finally, wrap things up with decentralization and consensus.
Section 1. The Decentralized Digital Ledger.
Before we get completely lost in the microscopic details of hashing and nodes, we really need to establish the foundational big picture here. At its absolute core, a blockchain is exactly what it sounds like. It's a decentralized, distributed, and immutable digital ledger used to record transactions across a vast network of computers. Think about a traditional database managed by a central authority, like a bank or a government. A blockchain flips that completely upside down. It relies entirely on cryptographic math and network consensus to establish trust. There's no middleman, no central intermediaries. It is simply a shared record-keeping system where the network itself is the ultimate source of truth.
Moving on to Section 2, Inside the Block Anatomy.
Let's actually pop the hood and look at a single block. Every block in a blockchain is built from three primary elements. First up, you have the data. For financial blockchains like Bitcoin, this is the who, what, and how much, the sender, receiver, and transaction amount. Second is the hash. You can think of this as a completely unique digital fingerprint for that specific block. And third, and this is absolutely crucial, is the hash of the previous block. This right here is the magic chain link connecting everything together. Oh, and a quick fun fact. The very first block in any blockchain doesn't have a previous hash to point to, so it gets a special name. We call it the Genesis block.
And this brilliantly illustrates exactly how all that raw transaction data gets organized inside the block. This structure is called a Merkle tree. A single block might contain thousands of individual transactions, but instead of clunkily hashing one giant, massive file, a Merkle tree efficiently pairs and hashes individual transactions layer by layer. It moves up the tree, sort of like a tournament bracket, until it condenses thousands of hashes into one single master root hash at the very top. It's just an incredibly efficient way to summarize a massive data set.
Now, all of this critical metadata gets stored in a very compact summary called the block header. It holds the version, the previous block hash, that Merkle root we just talked about, a timestamp, the difficulty target, and a random number known as a nonce. And here's where this matters. Miners actually do not hash the entire block of raw transactions. That would be ridiculously slow. Instead, they only hash this tiny, compact block header. Doing it this way massively improves the efficiency of the entire mining process.
Section 3. The Immutability Mechanism.
Let's see how this all builds into the security engine, using exact cryptography to make these blocks virtually tamper-proof. The absolute star of the show here is the SHA-256 algorithm. It's a one-way cryptographic hash function. What does that mean? It means it can take an input of literally any size, run the math, and produce a fixed 64-character output. But the critical thing to remember is that this is a strict one-way street. It's totally irreversible. You absolutely cannot reverse engineer the original transaction data just by looking at the output hash.
Now, what's really interesting about this slide is a concept known as the avalanche effect. Let's say you take a massive document and you change just a single period at the very end. The algorithm doesn't just change one character in the hash. It alters roughly half of the 256 bits in the resulting output. Even a microscopic single-character tweak creates a completely unrecognizable and totally different digital fingerprint. And this avalanche effect triggers a powerful chain reaction that protects the whole network. Let's walk through it. Imagine a hacker decides they want to cheat and alter a transaction back in block 2. Instantly, because of the avalanche effect, block 2's hash changes completely. But wait, block 3 relies on the original hash of block 2 to form its chain link. So block 3's previous hash record is immediately invalidated. Every subsequent block just shatters. To successfully pull off this hack, someone would have to recalculate every single hash forward in the entire chain, which demands an impossible amount of computing power.
Section 4. The mempool waiting room. We've talked a lot about how blocks are secured, but what about the engine's fuel line?
Where exactly do transactions wait before they enter a block? What does the life cycle of a digital transaction actually look like the very second you hit send on your crypto wallet? Well, they go directly to the mempool, short for memory pool. This is a decentralized staging area for unconfirmed transactions. Think of it as a giant digital waiting room. Since block space is strictly limited by the protocol rules, validators simply can't process everything at once. They have to pick and choose. And because validators want to maximize their own revenue, they naturally prioritize transactions that have the highest attached fees. So the mempool isn't just a waiting room, it's an open market where transactions actively compete and bid for block space. Section 5, Decentralization and Consensus. Let's zoom all the way back out to the macro level now. We know how blocks are built, we know how they're secured, but how does the entire global peer-to-peer network agree on what the final truth is, without a boss telling them what to do? When a new block is mined, it doesn't just magically become truth. So the crucial point is the verification pipeline. The block gets broadcast out to the entire peer-to-peer network. Every independent node validates the block for themselves. They check the cryptographic signatures, ensure balances are right, and make sure hashes actually match up. Then, consensus rules are applied. If more than 51% of the network agrees the block is perfectly valid, boom, it's permanently written to the ledger, everyone holds a copy, and everyone verifies the work. To stop bad actors from just spamming the network with fake blocks, networks like Bitcoin use proof of work. This is a consensus mechanism that requires miners to expend actual real-world computational energy to find that specific random number, the nonce, to validate a block. Miners use heavy brute force computation to guess trillions of numbers a second. It's basically a global lottery system. And what this elegantly does is anchor the digital security of the blockchain to a physical, highly tangible resource, electricity. But you might be wondering, what happens if two miners hit the jackpot and find a valid hash at the exact same millisecond? Well, the network temporarily splits. Some nodes accept one block and others accept the other. But the protocol resolves this beautifully with one simple rule. The longest chain wins. As miners keep working, one of those two chains will eventually get the next block added to it first. The shorter, losing block becomes an orphan block. But don't stress, the transactions inside that orphan block aren't lost forever. They just simply bounce back to the mempool to be picked up in the very next block. Which leaves us with a pretty provocative final thought. The Bitcoin network's total energy consumption is estimated at an astronomical 130 to 200 terawatt hours per year. That is literally comparable to the electricity use of a mid-sized country. So the big question is, does this massive physical energy cost of proof of work truly justify the ironclad global security it guarantees? It's a fascinating debate about the real-world trade-offs of true decentralization. And honestly, it's the exact reason why alternative mechanisms like proof of stake were developed. I really hope this explainer helped you grasp the incredible engine driving blockchain technology. Keep learning and keep questioning exactly how our digital world is being built.